All right. Alrighty, good morning, everyone. Welcome to Brick as a Sustainable Material presented by Stephen Judd. Today, everyone is in listen-only mode, so feel free to type your questions in the chat, and Shannon Perry will be monitoring this chat box throughout. Thank you all for coming, and thank you, Stephen and Shannon, for presenting today and helping out.
Well, thank you, Isabella, and thank you, Shannon. Like you said, Shannon will be monitoring the chat box. And we will go ahead and get rolling. So thanks for being here. This presentation of brick as a sustainable material, and the sort of byline that will be used throughout is make it once and use it forever, because it is a very long-lasting and durable material. As far as the topics that we're going to be going over, we're going to talk a little bit about definitions and history of brick, the energy to produce and the carbon footprint, all sustainable issues. We're going to do a quick comparison of a building study using 3 different systems to see what the sort of energy use and carbon footprint is for those. We're going to talk a little bit about the energy codes and compliance. Briefly, we'll also touch on maintenance, and then end of building life. Notice I didn't say end of the material life, because brick does have an extremely long life, and a little bit about durability. So as far as definitions go, sustainability has multiple definitions. It can be the ability to meet the need of the present without compromising the ability of future generations to meet their own needs, using resources efficiently while balancing the environmental, social, and economic impacts, the ability to be maintained at a certain level, and the avoidance of the depletion of natural resources in order to maintain an ecological balance. So brick has been found at the ancient site of Jericho, dating back 7,000 years. This is an example of one of those types of bricks. Doesn't look like the bricks we use today, and obviously this has had some significant weathering over the last 7,000 years. Fired brick dates back almost 5,500 years, which allowed the brick to be made in cooler climates. Previously, it was just typically made in the warmer climates near the equator, where there's more sun, in order to typically bake and dry the mixture of mud, which was typically clays, used to make those bricks. Fired brick has been used in Rome, dating back over 2,000 years. And bricks have been used in the Great Wall of China, which is over 700 years old. Not many other building materials have that kind of a history. And more indigenous to the US, we have the indigenous peoples. This is a shot from Mesa Verde in southern Colorado. These basically adobe bricks are from 900 to nearly 1,300 years old. No other building material lasts longer than brick, with the exception of some stones. Not all stones. Some stones do not weather very well, like some of the sandstones. Marbles, depending on the atomic structure of the material, have thermal hysteresis problems, which causes them to bow. There was a famous building in Chicago that had to be reclad because all the marble was bowing and failing the connections and falling off the building. Brick doesn't have those problems. The National Institute of Science and Technology states that brick can often be in service more than 100 years, and maybe a useful life of 200 years is assumed. Older brick, again quoting from NIST, older brick buildings are adapted to new uses, with the existing brick walls included as a design feature. Here's an example of a railroad maintenance building. It was originally built in 1912. It was repaired and restored in 2002 and was reopened as convention space in 2004, and it's still in use currently. Most brick walls have little maintenance, repointing of mortar joints on portions of the wall, anywhere from 25 to maybe 50 years. So this particular building is 111 years old and still going. And here's a building across the plaza from the maintenance building. This is a 28-bay train engine maintenance roundhouse, also built in 1912. It's been restored and is being used as a museum space. Gorgeous looking structure. This is all actually unreinforced brick, multi-wide brick walls. And again, 111 years. So there's a famous building in Chicago called the Palmer Hotel. It had its grand opening on September 25th, 1871. Unfortunately, 13 days later was the Great Chicago Fire, and the hotel burnt down. And it was rebuilt a little over 2 years later in November of 1873. And in their marketing, they said it was built of brick and iron and was the world's first fireproof building. It is the longest continually operating hotel in the United States. So it's 150 years old and going strong. I was just there for a conference recently. It's a gorgeous building. Another building happens to be in Chicago, is the Monadnock building. The phase one, or first half of the building, which ran roughly half a city block long, was built in 1891, all load-bearing brick masonry. Phase two was completed in 1893. It's the back half of the building where you can see the cornice up at the top of the building was added. It is still the tallest load-bearing brick building in the world, which basically the north half. The south half is a steel-framed building carrying the gravity loads of brick veneer. And when it was built, it was the largest office building in the world. Here's a current shot of that exact building. The base of the building, the walls are about 6 feet thick, multi-wide, said load-bearing masonry. It's 132 years and still fully operational. So what happens when wood structures catch on fire? Here's an apartment building under construction. Here's another apartment building. This required the evacuation of adjacent buildings. And for all its interest in carbon sequestration and so forth, when wood burns, it returns the carbon to the atmosphere. That's not very often discussed, but that is in fact the case. And it stops sequestering oxygen as soon as you cut it down and make it into construction material. And for those who use wood burning stoves, when trees are burned, they generate more CO2 emissions per unit of energy than fossil fuels. So they actually contribute to more of the carbon problem in the atmosphere than any other fuel. Brick doesn't burn. Here's an example of a building that was undergoing renovation. And unfortunately, the interior roof framing caught on fire, not unlike what happened in Notre Dame in Paris a couple of years ago. A couple of days after the fire, this is what the interior looked like. The brick walls were still standing. They were a little bit scorched with soot. The top of the walls were covered to protect the brick from the weather. The owner of this building determined that they wanted to reuse this building and repurpose it. So they cleaned up the brick. They excavated below the building, shored it up, poured a 2-story underground garage underneath it, set it back down, finished the interiors, and this is what it looks like today. It's fully functional. All of the original brick exterior walls were reused, and it's a prime example of the sustainability of brick. It can weather extreme events and not have any problem with it being reused, generally speaking. So we're going to talk a little bit about the resources and energy it takes to make brick as compared to other construction materials. So in order to produce brick, it takes 7,182 megajoules per cubic meter of material. So when you're producing the brick, that's the amount of energy it takes. So that's kind of a meaningless number all by itself. So a megajoule is 1,000 joules, and a joule is a measure of energy or the amount of work done. So the amount of energy it takes to produce work or to make this particular material. And 1 joule is roughly 0.74 foot-pounds of energy. So that means the amount of energy to move a 1-pound object 1 foot. That's you're measuring the energy or work to produce this material. Cubic meter is a little bit larger than a cubic yard. So if you look at this in the Systems International units, 7,186 megajoules per meter cubed is really around 4,000 foot-pounds per cubic yard. So let's compare this with some other materials. So concrete reinforced with 1% reinforcing is roughly 5,500 megajoules, which is maybe 70% of that for brick. For a more heavily reinforced concrete structure, you're up around 8,500, which is roughly 20% more energy to produce those materials than brick. Let's look at glass, 71,000 megajoules per meter cubed, which is 10 times the amount of energy per cubic meter of material as compared to brick. Steel is 306,000 megajoules, which is 42 times the amount of energy that it takes to produce brick. And aluminum is 970,000 megajoules per cubic meter, which is 134 times the amount of energy to produce the same volume of brick. So you can see in this comparison that the manufacturing of brick uses a lot less energy per volume of material than any of the other standard construction materials that are used for the enclosure of a building. That speaks volumes to its sustainability. It's using a lot less energy per volume of material that's made. So let's look at the carbon footprint of making brick. So from one resource, it says there's 345 kilograms per meter cube. Again, a kilogram is roughly 2.2 pounds. Cubic meter is a little bit larger than a cubic yard. So 345 kilograms per meter cubed is roughly 584 pounds per cubic yard. This is of carbon produced or released into the atmosphere per cubic yard of brick material made, which gets down to a more sort of useful terms of 21.6 pounds per cubic foot. So a fair amount of carbon released in the atmosphere. So let's do the same comparison. So reinforced concrete is roughly 635 kilograms. So twice that of brick. There is some information in the industry that says 345 is actually a little bit low. It's maybe more like 600 kilograms per cubic meter. So it's a little bit less, 6% less than reinforced concrete. Compared to glass, 3,600 kilograms, which is 6 times the amount of carbon released into the atmosphere to make a cubic meter of glass as compared to brick. Steel, 12,000 kilograms, which is 20 times more carbon released into the atmosphere to make steel. And aluminum is 18,000 or 30 times the amount of carbon released into the atmosphere to produce 1 cubic meter of brick. So the materials aren't used in equal quantities, obviously. A brick wall is thicker than a glass curtain wall. So what we want to do is a real quick comparison of a particular building type and look at a couple different scenarios of the energy it takes to produce the materials to enclose a particular building. So the building we're going to look at is going to be sort of a big box store. It's 100 feet by 200 feet, 18-foot tall walls, and an 80-foot wide storefront at the main entry. Most box stores have large sort of vision glass areas or supermarkets. And it's got a typical steel framed roof. So the first option we're going to look at is going to be a building with 8-inch structural brick reinforced walls, which is similar to CMU, reinforced with number 6s of 48 inches on center each way. And there's no additional exterior lateral force resisting systems that are required to be added because the reinforced masonry does all of that work as a bonus to being the enclosure of the building. And we're going to compare that to an option of a brick veneer over 6-inch steel studs, which are probably a little bit light in this case for an 18-foot tall wall. And it does require some additional bracing to resolve the lateral loads. So it's got a little bit heavier roof framing system. So here's a view of the two buildings we're going to look at. They both have steel framed roofs. We've got reinforced masonry versus veneer over steel studs. This one has roughly 12 pounds per square foot of roof framing, which includes any internal bracing within the roof system that's necessary. And again, all of the lateral loads go to the exterior walls and down because those are reinforced masonry walls. And this takes 6.1 thousand megajoules of energy to produce those structural elements from the ground up. This doesn't include the foundations, which would be fairly similar in both cases. And we're going to compare that to the brick veneer building with steel studs, which takes 7,000 megajoules to produce the structural elements of this particular building, which is roughly 14% more energy required to do the brick veneer building over the structural brick building. And just as a comparison to try and extrapolate this to other building systems, let's say it's a glass and aluminum curtain wall building. Not that it would look like this, but just as a comparison. So if this had a curtain wall system or a storefront system all the way around the perimeter, it would take 11.15 million megajoules of energy to produce those structural elements, which is almost double the amount of energy it takes to do the reinforced structural wall system. So you can see that by comparison, a structural masonry wall consumes a lot less energy. It's a lot more sustainable. It's preserving more energy for other uses than other systems to produce this particular building type. Something to remember: more mass, less glass. Glass costs more energy, produces more carbon in the environment per cubic meter, and it causes more air conditioning and heating demand because its thermal properties are nowhere near the thermal properties of the other two systems we discussed. And as walls get taller, changing from a brick veneer with steel stud backup to a reinforced brick veneer with light gauge steel framing actually becomes more economical. So the interior studs can be 22 or 25 gauge, just like typical interior stud framing, because the reinforced veneer is actually doing all the work of resisting the environmental loads, both wind and seismic loads, as well as the barrier for thermal, keeping the heat and the cold from outside from getting to the inside. So at a certain point, somewhere between 16 and 18 feet, it's actually more economical to go to a reinforced brick veneer than to heavier gauge studs like 16 or 14 gauge, or maybe even 12 gauge studs that are 6 or 8 or 10 inches deep. So more mass, less glass. I'm going to talk a little bit about energy use here and some energy code stuff. It says 30% of the energy used in the US is for building use, and the majority of that is for tempering the interior space. the heating, ventilating, and the air conditioning systems. So if you can positively affect the need of those buildings to use that energy for heating and cooling, you're being a more sustainable material and you're using less of the resources available. So in evaluating building types, look for the environmental impact of the various components. Structural brick is a very economical, eco-friendly material. So let's look at benefits of brick veneer, for instance. Most model energy codes and code check systems do not account for the thermal benefits of brick veneer. The prevailing theory is that the airspace behind the brick isolates the brick from the wall, so the brick has no value. But in reality, testing has proven that the brick veneer actually significantly impacts the thermal performance of the wall in total to a very positive way. Recent modeling has shown this for vented or ventilated brick veneer. So a vented brick veneer has vents at the base where the weep systems are, and a ventilated system is a brick veneer wall with vents at the top and the bottom where you think you would get some convection currents and so forth, but they perform almost identically. And the fact that the brick veneer is so effective, it's more valuable as a sustainable material and requires less energy demand on the building. So according to the current energy codes, the US and Canada are divided into various climate zones. So in the US, we go from zone 1 through 8. Zone 1 only occurs in Hawaii, the very southern tip of Texas, and the very southern tip of Florida. And zone 8 only occurs in the upper portions of Alaska. And for Canada, they have zones 4 through 8, and they've divided their zone 7 into a 7A and a 7B, but they relate and match the climate zones that are used in the United States, as you can see from this map. And so each climate zone has its own energy requirements. Obviously, the farther north you go, the more heating demand there is, and the farther south you are, the more cooling demand you have, but they both affect the amount of insulation that's needed in the exterior walls of the building. So the requirements to meet the energy codes are based on conformance paths. The most often are used are prescriptive requirements, and what's becoming more popular is the energy trade-off requirements, where you can take maybe a system that's performing better than required, like a wall system perhaps, and then you can reduce the amount of insulation required in the roof system, for instance, so that the average of the use still is within the compliance mode. But more often than not, typically, if you increase the insulation in the ceiling or roof, you can conversely decrease the amount of insulation you may need in the walls and still reach a compliance situation. So we're going to talk about climate zone 5, which is a broad sort of band across the upper Midwest, going up into the northeast and all the way up into the northern part of Washington state. And the United States is divided into sort of 3 zones. There's the marine zone over on the west coast for sort of the upper 2/3 of the west coast. Then you've got the Intermountain West, which is considered a dry zone. And then from the Midwest over to the East Coast, it's considered moist. But in the code that we're using, this is from ASHRAE, which is also similar to the International Energy Conservation Code. In climate zone 5, which we're talking about, all the prescriptive requirements are here. So for non-residential buildings, which means basically commercial, you've got different amounts of insulation or U factors that are required for metal buildings, steel frame buildings, wood frame buildings, and other, which happens to be exactly the same values for residential. The difference comes in when you're talking about mass walls. There you require a little bit more insulation or a lower U factor for residential than you do non-residential, perhaps because commercial spaces are only occupied for a certain portion of the day, whereas residences are typically occupied for larger portions of the day. So we're going to talk about the heat flow transmittance, or the U factors, which is a maximum value that's allowed. And conversely, it's related to the heat flow resistance, or the R value, which has minimum amounts of R value that are required for a particular wall type. In this case, these are all walls above grade that we're looking at here. So for wood framed and other, you can see that you've got the R13, which is for a 2x4 wall, needs an additional space between the studs filled with R13 insulation, typically fiberglass bat insulation. And then in addition to that, you're required to have a 7.5 R value of continuous insulation, either inboard or outboard of the framed wall, for a total R value of 20.5. And then if you have deeper studs, 2x6 studs, you have R19 between the studs, in addition to an R5 of continuous insulation on the outside, typically of the wall. If you look at steel framed walls, so light gauge steel framing, they only give you values based on a 4-inch wall. So you have R13 plus R10 for a total of R23. And we're going to jump up to a mass wall, because that's where we're going to be talking about how the effective brick. So here you can see that the code acknowledges the fact that brick has some special properties that help reduce the amount of insulation that's required. So you look at under the left-hand columns, non-residential, you have an R of 11.4 continuous insulation versus the combined insulation of either 23 or 20.5 or 24.5. And then for residential, it kicks up just slightly for an R value of 13.3. So two of the programs that the government has written, one of them is called ResCheck, for Residential Energy Compliance Check. It uses the International Energy Conservation Code. And when you go into the program, it gives you these options for walls. It talks about masonry block, which is typically CMU. And you can see that there's no brick veneer over stud framing. So you have to go down and pick the other option, which gives you the options of looking at a framed wall, a mass wall, or some other defined wall system. We jump over to ComCheck, which is for the commercial buildings. It typically is based off of ASHRAE 90.1, which is allowed by the International Energy Conservation Code as an alternate compliance mode. And here you go to the exterior wall systems, and again, you don't see any options for brick veneer over stud framing. So you pick the other category, and you're given these options that you can pick. But you have to input certain data to go through this process. So we're going to talk about that real quick. This is just a thermal modeling program written by the National Brick Research Center. And this particular wall is a 3/8 inch vinyl on the left side, over 5/8 inch OSB, over 2 inches of polyurethane exterior insulation, over the wall sheathing, another layer of 5/8 inch OSB, R15 bat insulation with 4-inch steel studs, and a 1/2 inch interior sheetrock. And we're going to compare that to a typical brick veneer wall, which has 3 5/8 inch brick over a 2-inch air cavity. And here we're only going to use a 1/2 inch polyurethane insulation. Then the same OSB, same R15 interior insulation in the cavity, wall cavity, and interior sheetrock. So when you go through the analysis over here on the vinyl wall, we've got R10 for the exterior insulation. We've got R15 for the wall insulation. And it gives us an equivalent R value of 21.26. Well, why isn't it 25? Because 10 and 15 is 25. Well, the steel stud framing is a thermal bridge, which reduces the effectiveness of the R15 insulation in the wall. So that drops it down quite a ways, but we're picking up some additional insulative value of the 3 layers of sheathing, the 2 OSB layers, plus the interior sheetrock, and a very minor contribution of the vinyl finish on the outside. So we're down to 21.26. Now we compare that to the brick veneer wall. We've got R2.5 on the exterior, R15 in the wall. Gives us a net R value of 11, almost 12 for that system. And again, it's not 17.5 because there's less insulation on the outside and the thermal bridging of the steel stud. So for climate zone 5, let's see how it compares. So for a steel framed wall, we need an R of 13 plus 10, so we comply with that. So that's good. And we look at the maximum U factor that's allowed, which is the inverse of the effective R value. So 1 over 21.26 is 0.047. That's less than 0.055. So that complies with the code. Let's look over here at our brick veneer wall. So we have an R of 11.4 continuous insulation. On the outside, we only have 2.5, so we don't meet that criteria, although the combined insulation theoretically is 17.5 with an effective R value of roughly 12, which exceeds the 11.4. But we are under the maximum U value, so this then reaches compliance using brick as a mass wall. So to consider a mass wall, you have to look at 2 things. The heat capacity of the wall has to exceed 7 BTUs per square foot per degree Fahrenheit. And we look at this analysis of this wall and we have a heat capacity of 7.108, which exceeds 7. So it meets the criteria to be considered a mass wall. This is something that most people do not understand or are not aware of, is that the addition of the brick veneer actually creates a mass wall scenario, which reduces the demand of insulation on the wall because of the performance that the mass of the brick provides. The other option is if you have lighter material, not greater than 120 pounds per cubic foot, you have to have at least a heat capacity of 5. So we already know we have a heat capacity of 7, so we need to check to see what the unit weight of the wall is. So we add up all the wall thicknesses. We got 3 5/8 for the brick, 2 inches for air, 1/2 inch for insulation. I threw in 1/8 of an inch for the weather resistant barrier. Then you got the exterior sheathing at 5/8, 4-inch studs, 1/2 inch interior sheetrock is a total of 11.375 inches, or roughly 9.5 feet thick. And we look at the weight of the wall. So we've got 29 pounds a square foot for the brick, 2 for the ties, 0 for the air, 1/2 pound a square foot for the 1/2 inch insulation, 2.3 for the exterior sheathing, 1.5 for the stud framing, 1.0 for the interior insulation in the cavity space, and 2 pounds for the interior sheetrock. We end up with 38.3 pounds a square foot for the wall, divided by the thickness gives us a unit weight of 40.4 pounds a square foot. It's less than 120, so all we need is a heat capacity of 5, and we have 7. So both checks confirm the fact that this can be considered a mass wall, which reduces the demand of insulation on the wall, which reduces the material used to comply with the code. It's a more efficient energy conservation system. Again, more mass, less glass. So the use of brick veneer can reduce the insulation demand of the exterior wall just by adding the brick veneer, which is commonly not accounted for in the energy code checks. So we can help with that if that ever becomes an issue. We have the information, the data to help you walk through that with owners and designers. And let's talk briefly about maintenance. The lower the maintenance, the more sustainable it is because you're using less materials to maintain the building. So typically, the most routine maintenance that is needed is repointing depending on the type of mortar. And this can be anywhere from 25 to 50 years that occurs depending on how harsh the environment is. A lot less routine cleaning than a glass curtain wall system, for instance. And this conserves resources, so it makes brick a more sustainable material. Let's talk about what happens at the end of a building life. Notice, again, I didn't say end of the life of the brick. So when a building has served its useful purpose, it can be more expensive to maintain and restore the building than to just demolish it and put something up in its place. So in most cases, unless it has high historical significance, it's going to be demolished. And when that happens, those materials that were used to build the building are pretty much damaged beyond the ability to reuse. So you can't just generally pull them off of one building and put them on another building. They're salvaged, they're typically broken or shredded into small bits. And then for aluminum, steel, and glass, they're melted down, which uses a lot more energy, and reformed and reused. And this also pumps more carbon dioxide into the environment. For concrete, unless it's used as a landfill, it's typically broken up, crushed, or washed. And that also takes energy and resources to reuse those materials. So let's look at brick. It can be salvaged, reclaimed, or repurposed without significant energy consumption. Here's a pile of brick from a demolished wall. We have show laborers here going through and picking through the brick, removing the mortar that's adhered to the brick, palletizing it according to color, so that it can be repurposed as a commodity and bought and or sold, just similar to newly manufactured brick. And here is a residence that used salvaged or recycled or reclaimed brick for their exterior wall system. No additional large amounts of energy to use this brick because it was already manufactured years and years ago. And resalvaged, recycled, repurposed brick obviously is not required to meet the new manufacturing requirements for manufactured brick, although it may be important to know the properties of the brick depending on where it's being used. So it's a good idea, if it's going to be in cold climates where you've got freeze-thaw cycling, to have the brick tested to see how it compares for durability in relation to what the requirements for a newly manufactured brick would be. So typically the durability indicators are the compressive strength and the absorption. And you can also do freeze-thaw testing to determine the durability of the unit. So that's something to keep in mind if you're reusing or intending to use recycled brick. And recycled brick travels, just like other brick. This is an example of a diagram showing where brick either was sent or retrieved from in relation to the Chicago market. So if you want a particular color that's indigenous to a particular area, then, and you want recycled brick, then you have to go to those areas where it's being used. Brick is very much driven by the materials that are close at hand to the brick manufacturer. So certain colors, especially historically, can only be obtained from certain areas for the recycled and reused brick, because the clay material is indigenous to different areas, different colors. So we're going to talk a little bit more about the resiliency and durability of the brick. What is better for sustainability than a structure that is not damaged by extreme environmental events? It remains standing and functional during the recovery periods. That's why the code requires certain buildings to be what's called essential facilities, so that after the design event, whether it's a tornado or a hurricane or an earthquake, they remain functional to help the recovery process. So reinforced hollow clay masonry, which is abbreviated as RHCM, has been subjected to and passed many extreme event tests. So we're going to talk about those. So fire test, a tornado projectile test, a 17 protocol ballistic resistance test, and not a blast test that I'm aware of yet, but there are some in the planning stages, but it has been used for blast design. So for UL fire test, the wall was constructed, reinforced, placed under load. So there's jacks compressing the wall, and is put onto a fire chamber, which ramps up to a heat of 2,000 degrees on one side of the wall. Thermal couples on the back side of the wall measure the temperature. And when any one thermocouple hits 350 degrees, or the average of all of the thermocouples averages 250 degrees, that marks the time duration of the test. And it goes in 1 hour increments. So if it so happens that the test lasted 1 3/4 hours, that's still a 1 hour wall. And in this particular instance, this was rated as a 4 hour wall. Then after it's heated, they take the wall off of the chamber and shoot water on it as a firefighter would, and trying to control the fire under a stream of 45 psi. So this wall was tested that, and it was rated as a 4 hour wall. You can see a video of this test on the Interstate Brick website if you're interested. And here's an essential facility built out of reinforced structural clay masonry, and this just happens to be a fire station for fire rated brick. Here's the projectile test for the FEMA tornado criteria, where you take a 10-foot long 2x4 that weighs 15 pounds. You shoot it at the wall at 100 miles an hour in 3 different places. And if it penetrates the wall or passes through the wall, which it does for vinyl siding, no shock there, does for stucco, and sometimes for even brick veneer, that's considered a fail. So it has passed this test, and you can also see a video of this test if you're interested at the Interstate Brick website. And here's a facility that's a tornado shelter built out of reinforced clay masonry. In this particular instance, the building is circular. So the walls were built first, all the way up to the top of the wall. Then the single ply membrane roofing was attached, and then blowers were put on the doors, the windows and vents were sealed, and they inflated the roof into the shape you see here. And while inflated, they reinforced it and put shotcrete or gunite over the interior surface of the roof, allowed it to cure, then took the fans away. It's self-supporting at that point, painted the interior, and they're done. This serves as a community tornado shelter, as well as a gymnasium for the local high school. And it's built out of those hollow clay units. And here's the testing protocol, which was a conglomeration or mashup of UL testing protocols, ASTM testing protocol, the Department of State testing protocols, and the Department of Justice testing protocols. And sometimes they overlapped and sometimes it didn't. In addition to those, we also added some armor piercing rounds. Here's a larger list of the 17 munitions that were tested. So there's short barrel rounds, pistols, long barrel rifles, and shotguns. And it went from 22 caliber all the way up to 50 caliber, and then 3 different protocols for the shotgun. And it passed all those. Here's some images of the testing that was occurring. And from the muzzle to the face of the wall was 15 feet. And there's also a video of this on the Interstate Brick website, if you're interested. And then blast design. So on the left, you see a post and beam framing system. And on the right, you see a reinforced masonry wall. If you have a blast for some unpredictable reason, You can get significant collapse, which occurred in Oklahoma City, the Frederick Murrow Federal Building, whereas you have a very contained amount of damage in a reinforced masonry wall because of the inherent arching action that occurs in masonry construction. So you may have some damage, but you're going to have significantly less damage in a reinforced masonry wall system than in a post beam framing system. And here's a federal courthouse in Kentucky that was built with reinforced brick veneer system that meets the GSA blast requirements for that facility. And just a few miscellaneous items. We're nearing the end here. Brick is the essence of sustainable materials. It's one of the lowest energy uses to manufacture. It reduces energy when it's used in the exterior wall of a building. It has low maintenance. It's long lasting. It's durable, resists fire, impact, ballistics, mold, mildew, rot. Doesn't smoke or release volatile organic compounds. It uses very little energy to salvage and reuse, provides thermal mass, which helps moderate the interior temperatures of a building. It's beautiful to look at. On the left, you see a 17-story hotel built with all reinforced structural clay masonry and poured-in-place concrete floors. On the right, you see a 17-story reinforced brick veneer apartment building. And it's insect proof, so you don't need to waste any time or energy and materials dealing with those sorts of things. There was a school district in Houston that was getting ready to open when one of the hurricanes hit 2 weeks before the opening day of school, flooded numerous facilities in this particular school district, so they had to delay the opening of the school by several weeks while they pumped the water out of the buildings after the hurricane had passed. Then they had to rip out all of the sheetrock on the partition walls, had to deal with mold and mildew abatement, and then rebuild the walls. If those interior walls had been made with reinforced masonry, they would have basically had to pump the water out, wash the walls, and it's ready to be reoccupied. A significantly shorter down period for the use of masonry. And let's talk about maybe a story you heard a long time ago about 3 houses built by some brothers. There was a straw house, a wood house, and a brick house. Then along came an extreme wind event called Big Bad Wolf, and it ended up with a pile of straw, a pile of wood, and the brick house was unharmed. That same lesson still applies today. Durable structures enhance sustainability. More mass, less glass. So a couple of shots of some unique uses of masonry, and why not use masonry in buildings. I'd like to thank the owners, developers, designers, contractors, manufacturers, masons, bricklayers, and allied craft workers who make a better built environment with brick. Thank you. This was a shot that I came across my desk yesterday. Hey, ChatGPT, finish this building. Point is, skilled craft workers are irreplaceable. They're needed to build a better built environment. Thank you. And that's all, folks. We have a few minutes for questions.